By the end of this video, you will have good understanding on fundamental math required for DSA. Usually when they ask you a question, it will be indirectly dependent on math. So the primary topic will be something else, but you will be needing math to solve that problem. That is why it is very important to create good strong foundation in mathematics. First thing that we are going to look is floating point numbers. Usually in competitive programming, you have two different options, a 64-bit double and 80-bit long double. Let's say you initialize the value of x, something like this. So 0.3 into 0.3 plus 0.1, which is 1. But due to the rounding errors, the value of x might be smaller than 1. And if you use equal to operation, it might be very risky. So let's say you initialize x as something like this, and then you write a if condition where it says x equal to 1. And this will fail. Why? Because x might be smaller than 1 because of rounding errors. So what to do? Well, we are going to focus on calculating the differences. So this is what we will check. If x minus 1 is less than or equal to some very small number, 10 to the power minus 6. Usually they call it epsilon, a very small number. But that's what we are going to do. We are going to compare the differences, not the actual value. I hope that makes sense. All this usually happens in a geometry type of problems where they might ask you to compute an area or a distance between 2 points or distance between 2 lines. There you might write a perfect code. Your code will work on given sample test cases, but it might fail on actual test cases because you might have used this operation in your code, and that might fail because of rounding errors. Always remember, it's always better to compare the difference. Let's go to the second topic, which is modular arithmetic. See, in modular multiplicative inverse video, we saw how to compute modular multiplicative inverse, right? That is a to the power minus 1 mod m. Now, just to highlight that a plus b mod m is going to be a mod m plus b mod m, then you can take the mod of whole result. Similarly, for a minus b as well, you can take a mod m and b mod m, and then you take the difference, and then after that you can take the mod of the result. Remember, if the result is less than 0, then you need to add m into that particular result. For a into b, you take a mod m, then you take b mod m, then you multiply, and then you can compute the modulo of the result. So sometimes what happens, the answer to a problem can be very large. So what they will ask you is to provide the answer modulo m. M usually is a prime number, and most of the times it will be 10 to the power 9 plus 7. Let's say a is 7, b is 2, and m is 6. And if you see a minus b modulo m, well, a mod m will be 1, right? B mod m will be 2, and 1 minus 2 you will get minus 1. Then you have minus 1 mod 6. Now this result is less than 0. So you need to add the value of m before taking the mod again. So minus 1 plus 6 is going to be 5. Then you take the mod. So there are primary 4 operations: addition, subtraction, multiplication and division. For addition, it's very clear, no problem. For multiplication, it's very simple, no problem. For subtraction, just make sure that value of result at any point of time should not be less than 0. And for division, you need to know how to compute modular multiplicative inverse. I hope this is clear. Let's look at some standard problems. This is sum of first n natural numbers. Proof is very simple. Look at this, 1 and n. If you club this 1 and n, it will be n plus 1. Then you have 2 plus n minus 1. If you club these together, if you add these together, you will again have n minus 1. So you are getting n plus 1 always by this logic, and you will have n divided by 2 pairs. That's why sum of first n natural numbers will be this. The next one is sum of the square of first n natural numbers. The formula is this. We can prove this by using the technique of induction. So this holds true for f of 1. right? F of 1 will be 1 square, it's going to be 1. You put the value of 1 here, so you have 1 into 2 into 3 divided by 6 and you will get 1. So for f of 1 this holds true. So let's compute for f of n plus 1. So what is f of n plus 1? Is just f of n plus 1 squared, right? So let's expand this. N into n plus 1 into 2n plus 1 divided by 6. I am just writing this particular value here. And n plus 1 square will be as it is. Now you can take this n plus 1 common from here and from here. So this n plus 1 is common now. So you have n plus 2n plus 1 divided by 6. This n is here, this 2n plus 1, this divided by 6. Then you multiply this by 6 and divide by 6. That's what we have done here. See, n plus 1 is here. You multiply by 6, you divide by 6. No problem. Remember, we have taken n plus 1 common from this expression and from this expression. Right? Now let's just expand this. So this is going to be 2 into n squared. This is going to be n. This is going to be 6n. And this is going to be 6. So you had 2n squared plus 7 plus 6. Right? You can write it as 2n plus 3 and n plus 2. Simple. So you get something like this, n plus 1, which is this one. You replace this entire with this. So you have n plus 2 and 2n plus 3 here, and you have divided by 6. So if it is true for f of n plus 1, we have proved that it will be true for f of n plus 1. And for the base condition f of 1, we know the value is perfectly right. So by using the induction, you can prove it for f of 2, f of 3, likewise f of n. And the formula is perfectly valid. Very simple proof, but technique is important. Here the technique is induction. Now we will understand arithmetic progression, geometric progression and harmonic progression. See, it's very simple. AP is very simple. Difference between the two consecutive number is going to be constant. It's like A2 minus A1 is going to be D. A3 minus A2 is again going to be D. A4 minus A3 will be D. Something like that, right? So the value of A of n is going to be A1 plus n minus 1 into D. Right? So if you observe carefully, an plus a1 will be exactly same as an minus 1 plus a2, because you are removing d here but you are adding d here. Here d got added, here d got subtracted. So the value will be exactly same. We have already done this. So now you know the value of a1 plus an is exactly going to be a2 plus an minus 1. Similarly, you know that this value will be equal to a3 plus an minus 2, right? So you can club these values together and you will have a1 plus a of n. Total number of pairs are going to be n by 2, because in every single pair there are two numbers involved. So that's how we get this formula. I hope this is clear. Then there is something called geometric progression, GP. We are going to multiply previous number by a constant value k. See, in AP the difference was constant. A2 minus A1 is going to be D. Here we are just multiplying every single number by k. So first number is going to be A1. A2 will be here A1 into k. A3 is going to be A2 into k. This is GP. We need to prove this sum of GP, right? It's very easy to prove it actually. So let's say you call it as f of n, right? This value. So you multiply on both sides by k. So you have k into f of n. And on RHS you have a into k plus a into k square plus a into k power 3. Something like that, plus a into k to the power n plus 1. You subtract equation 1, which is this, from equation 2. So you will have k into f of n minus f of n. This will cancel out this. This will cancel out this. Remember, we are subtracting, right? We are subtracting f of n from k into f of n. So this will cancel out this, and this will be cancelled as well by a to the power kn. So finally you will get something like a kn plus 1 minus a. You take k common, you have f of n into k plus 1 is equal to a kn plus 1 minus a. You divide k plus 1 and you have the formula that you needed. I hope this makes sense. It's very simple. We just wrote f of n as a plus ak squared. Then you multiply left hand side by k and you multiply right hand side by k. So now this a will become ak. This ak will become ak squared. Then you do a simple subtraction, right? K into f of n this minus f of n this. So this ak will cancel out this ak. This ak square will cancel out this ak square. This ak to the power 3 will cancel out this ak to the power 3. Similarly, everything will be cancelled. This will be cancelled by this. You will have a remaining and you will have a into k to the power n plus 1 remaining. So something like this, k into f of n minus f of n. You will have a into k n plus 1 minus a, right? You take this f of n common. So you have f of n k minus 1 equal to a k n plus 1 minus a. Now you divide this LHS and RHS by k minus 1 and you have the final result. Now for HP, we are not going to prove any kind of summation or anything. Rather, what we are going to prove is an upper bound of this particular value. Let's say you write something like this. Look at this. You write 1 here, you write 1 here. You write 1 by 2 here, you write 1 by 2 here. Now you have 1 by 3 here. I can write 1 by 2 here, right? Because we have less than or equal to sign. 1 by 3 will be less than or equal to 1 by 2 for sure. Again, for 1 by 4, you can write 1 by 4. But for 1 by 5, you can write 1 by 4. For 1 by 6, you can write 1 by 4. For 1 by 7 as well, you can write 1 by 4. For 1 by 8, you can write 1 by 8. For 1 by 9, you can write 1 by 8 here again. Till 1 by 15, you can keep on writing 1 by 8. So, this less than or equal to holds true. If you observe carefully, this value will be 1. This value, imagine here you have 1 by 7. Then you can write 1 by 4 as well. 1 more 1 by 4. This value will also be 1 now. So there are log n parts whose value is going to be 1. See, this is one part. Value of this is going to be 1. Then there is this part. 1 by 4 here, and I can write 1 by 7 here. It will be 1. For 1 by 8 till 1 by 15, I can just write here 1 by 8 plus 1 by 8 plus 1 by 8. 8 times, right? So you will again have one more part whose sum is going to be 1. So there are exactly going to be log n parts. So the upper bound for this particular HP is going to be log n plus 1. This is exactly what we saw in C of Eratosthenes, and there are so many algorithms and there are hundreds of problems that uses this technique to compute the time complexity. This technique is not asked directly but heavily used for computing time complexity. Always remember, when you have something like this, the upper bound is log n.